Hello, welcome to this video for uncertainties, and this is for level 3 physics for the investigation internal, the practical investigation, P3.1. What is uncertainty? So uncertainty is an estimate of the inaccuracy of a measurement during a practical investigation. For example, an uncertainty may arise when measuring the length of a rod due to parallax error. Another example is the human reaction error, where there is uncertainty due to the starting and stopping of the stopwatch. So basically, uncertainty is just used in the practical physics is when you have a measurement, but you know that measurement cannot be exactly precise. So you're gonna give an estimate of uncertainty. So it could be a bit more than the specified value or a little bit less than the specified value, and that's the uncertainty. So it's commonly used with the plus or minus sign. So with the plus or minus means it could either be a little bit greater than the specified value or it could be a little bit less than the specified value. So that's the plus or minus. The uncertainties in the practical investigation. So there are multiple ways of estimating an uncertainty in the investigation. So there's number one, and this is the most common one, it's a pre-investigation. So this method is involving estimating an uncertainty before the experiment, e.g., perhaps I'm doing an experiment where I'm trying to measure the period of oscillation of a simple pendulum. So because I'm timing something, I can say I'm going to estimate the average reaction error with the stopwatch would be 0.1 seconds or 0.2 seconds because that's the average human reaction error with the stopwatch. So that would be a pre-investigation because you're making that judgment, that average time judgment before you begin the investigation. So that's a pre-investigation. The advantages of a pre-investigation is that it's very simple, so you don't have to. So basically, you can just get it out and done. Get it out of the way before you start the experiment. The disadvantage is that it doesn't account for errors during the investigation. So, for example, I'm doing my simple pendulum investigation, and then I realized that it was actually a lot harder to time the oscillations for whatever reason, and I found that it was a lot harder to time the oscillations, which may have resulted in a larger human reaction time error, but that's a disadvantage for the pre-investigation because you've already set that human reaction error, the average human reaction error, before you've done the investigation. So that would be a disadvantage. Okay, so the second one you could do is half range. So this method involves taking half the range of the results as the uncertainty. E.g., if we have a set of data, 3 seconds, 2.8 seconds, and 2.9 seconds, the uncertainty is 0.1 seconds. So the largest value is 3 seconds and the lowest value is 2.8 seconds. 3 minus 2.8 is 0.2, taking the half is 0.1 seconds. So that would be the half range method. The advantages of this is more accurate because it can account for factors that are happening during the investigation because these are your results. The disadvantage of the half range method is that it could potentially result in a very large uncertainty if the range is too big. For example, if you had two sets of data and there's a pretty significant range in the data, then that's going to result in a very big uncertainty, which may decrease the reliability, well, not necessarily reliability, but decrease the accuracy of results because you have a greater uncertainty. Right, so determining uncertainties. So this is for pre-investigation. So if you're using a pre-investigation uncertainty, so in measurements, for example, the length of the string, we have to assume uncertainty 2 times the smallest division of the measurement. So we could be off on either side. So if you're, for example, measuring the length of the string, we could be slightly off on either side of the ruler. So for example, if we're using a ruler and the smallest division is millimeters, so the smallest scale on the ruler is millimeters, then we could take our uncertainty to be about 2 millimeters. We could be 1 millimeter off on either side. So the total uncertainty there is 2 millimeters. For timing, the average human reaction error is 0.1 seconds to 0.2 seconds, but that's also depending on the speed of the object. When I say the speed of an object, because timing is usually you need to stop at a certain time. So for example, in the simple pendulum example, we have to stop when, for example, after the pendulum has completed 10 oscillations. So uh, this human reaction error is very determined on how when you start and when you stop the stopwatch. So, for example, if the pendulum was moving very quickly, it may have been a bit harder to stop it accurately, which may increase the error. So, the average human reaction time error is just estimate based on the average. So, average is about 0.1 seconds, 0.2 seconds. Right, so if you're using masses, we should take the uncertainty of the masses furthest away from the set value and round to 1SF. For example, if we have if we have 10 masses in a 100-gram set, let's just say we have three examples, so 100.3 grams, 101.4 grams, 99.7 grams. The furthest weight that is away from 100 grams in this case is 101.4 grams, which means that the uncertainty is 1.4 grams, but we have to round. All uncertainties need to be rounded to 1SF. Remember, so all uncertainties rounded to 1SF, so 1.4 grams round to 1SF gives us just 1 gram. So that would be our uncertainty in that case. Alright, so when estimating the uncertainty before the investigation, try to estimate slightly higher. So it's always better to be too high than too low, but don't go overboard. So don't go like crazy. Don't say the uncertainty is like, for example, if you're measuring something, don't go overboard and say the uncertainty is like 5 centimeters, because that will result in your results having a very large inaccuracy, and then that might decrease the reliability of the results. So try to estimate like a bit more, but don't go too exaggerated, or else your results would be very fluctuated. Right, so we have absolute and percentage uncertainties. So the absolute uncertainty, so this is like the numeric uncertainty. So for example, in our last example, we had the measuring the string. Our uncertainty was 2 millimeters. So that our absolute uncertainty in that case would just be 2 millimeters. A percentage uncertainty, this is the uncertainty as a percentage of the actual value. So for example, that would be 23.12%. So this percentage is a percent of the actual value. So that would be the uncertainty. Absolute uncertainties in the final answer should be rounded to 1SF, and the actual value should be rounded to the same level as the uncertainty. So for example, if we had 4.8441 plus or minus 0.3311, so the uncertainty here, the absolute uncertainty is 0.3311. We need to round that to 1SF, which is just 0.3. And we've noticed that 0.3, that's in the tenths column. That means we also have to round our actual value down to our tenths column as well. So that becomes 4.8 plus or minus 0.3. Percentage uncertainty should be rounded to two decimal places when you're doing the calculations, but it should be converted back to an absolute uncertainty in the final answer. And when you convert it back to an absolute uncertainty, you have to remember to round it down to 1SF and then round the actual value accordingly. So converting between percentage and absolute uncertainties. So to convert an absolute to a percentage, we're going to say the absolute uncertainty over the actual value multiplied by 100. So basically, we're taking the ratio of the uncertainty and the value, and the multiply by 100 just gives us a percentage. To convert the percentage back to an absolute, so we just reverse the process. So we're going to say our percentage divided by our percentage divided by 100 multiplied by our actual value, and that will give us back our absolute uncertainty. And so here are a few practice questions. So for these practice questions, I want you to pause the video and try to convert whatever form I have it here. So if I have absolute uncertainty, you convert it to percentage. If the question has a percentage uncertainty, you convert it to absolute, okay? So question 1, we have 7.2 plus or minus 0.3 meters per second per second. Alright, so in this case, to convert this into a percentage uncertainty, all we need to do is we need to say 0.3 over 7.2 as a ratio multiplied by 100. So that will give us 7.2 meters per second plus or minus 4.17%. Alright, so the question 2, we have 43.2 newtons plus or minus 12.33%. Right, in this case, we have a percentage uncertainty, so we need to divide the percentage by 100. And once we divide the percentage by 100, we'll just multiply by our actual value, which is 43.2. So in this case, we'll get 43.2 plus or minus 5.32 newtons. However, we need to round all our uncertainties down to 1SF. 5.32, that rounds down to 5 newtons, and that's in the ones column, which means you have to round down our actual value down to our ones column as well. So 43.2 becomes 43 plus or minus 5 newtons. Question 3, we have 6.2 plus or minus 8.3 volts per meter. Right, so similar to the first question, we'll say that the ratio is 8.3 over 6.2, and if we multiply that by 100, we'll get our percentage uncertainty. So in this case, we'll have 6.2 volts per meter plus or minus 133.87%. Right, so manipulating uncertainties. So we have a couple of rules we need to remember. So when I say manipulating uncertainties, I mean adding to mathematically mathematically manipulating two uncertainties. So for example, adding two uncertainties, subtracting two uncertainties, and dividing and multiplying, and squaring and square root, and such like that. So rule number one, when uncertainties are added or subtracted, where absolute uncertainties are added. So for example, if I have a length that has some uncertainty and another length that has some uncertainty, if I add them together, then the value will add together and the uncertainties will add together. And that's the same for subtraction, but with subtraction, the actual values are subtracted, but the uncertainties are still added, okay? So uncertainties are always added, even if it's subtraction, okay? Number two, when uncertainties are multiplied or divided, their percentage uncertainties are added. Alright, so if we have, for example, an uncertainty divided by uncertainty, then we'll have the actual values will divide by each other, but the percentage uncertainties will add. Same with multiplication. If we multiply two uncertainties, the actual values will multiply, and the percentage uncertainties would add. And that's the same with a constant as well, because if, for example, if we're dividing by a constant, the constant will have no uncertainty, which means that the percentage uncertainty, so percentage uncertainty plus 0, that's still that percentage uncertainty. So but therefore we can just say if we're dividing by a constant, the value gets divided by that constant, but the percentage uncertainty stays the same. Number three, when the uncertainties are given to a power, the uncertainty is multiplied by that power. For example, if we have an uncertainty squared, then our value will be squared, but our percentage uncertainty will be doubled. For example, if we have a square root is the same as saying to the power of 1/2. So in that case, our value would be square rooted, but our percentage uncertainty will be halved. So number four, for the actual values, so I'm talking about the actual values. For example, the number that comes in front, do what you would normally do, okay? So just do what you would normally do. So basically, if we're adding two uncertainties, then you add the actual values. If we're subtracting, you still subtract. So everything with the front number there, you'll do the exact same thing. Alright, so a couple questions here. So we have question 1, so 5.09 plus or minus 0.62 joules minus 3.02 plus or minus 0.21 joules. So just try this question by itself first. Alright, so this actually relates back to rule number 1. So when we're subtracting uncertainties, the actual values are subtracted, but the uncertainties are added. So in this case, we'll have 5.09 minus 3.02 plus or minus 0.62 plus 0.21. So that will give us 2.07 plus or minus 0.83 joules. Number 2, we have 9.03 plus or minus 1.2 meters divided by 0.7 plus or minus 0.2 seconds. Alright, so this relates to rule number 2. So when you're dividing uncertainties, their percentage uncertainties will add. In this case, we have two absolute uncertainties, which means you have to convert both of them to percentage uncertainties first. Once we do that, we'll have 9.03 meters plus or minus 13.29% divided by 0.7 seconds plus or minus 28.57%. So now we can divide the two values, but we need to add the uncertainties. Add the percentage uncertainties. So we'll get 12.9 meters per second. So the reason it's meters per second is because we have meters over seconds. So meters at the top, seconds at the bottom, that becomes meters per second. Plus or minus 13.29 plus 28.57%, which is 41.86%. And once we have at this stage, we need to convert it back to an absolute uncertainty. So we'll divide the percentage by 100 and then multiply by 12.9. And we'll get 12.9 plus or minus 5.4 meters per second. But we need to round all our uncertainties to 1SF. So 5.4 rounds to 5 meters per second. And that's in the ones column. So we need to round our actual value to that ones column as well. So we have 13 plus or minus 5 meters per second. Number 3, we have square root of 99.2 plus or minus 9.3 hertz. Right, so square root is the same as saying to the power of 1/2. So once we have power to a 1/2, so we square root 99.2, and we need to halve the percentage uncertainty. We have an absolute uncertainty, so we need to convert it to a percentage uncertainty first. So in this case, we have 99.2 hertz plus or minus 9.38% to the power of 1 over 2, and then the percentage uncertainty is halved, and 99.2 is square rooted. We'll have 9.96 hertz plus or minus 4.69%. And we need to convert the percentage back to an absolute. We should get 9.96 plus or minus 0.47 hertz. Rounding it to 1SF, so 0.47 rounds to 0.5, that's in the tenths column. So we'll round our 9.96 to the tenths column as well. So we should get 10.0 plus or minus 0.5 hertz as our final answer. Question 4, 2.98 meters plus or minus 2.3% plus 3.12 meters plus or minus 2.4%. Right, so in this case, this applies back to our rule number 1. So rule number 1 says that when we add two uncertainties, then their absolute uncertainties will be added. Right now we have two percentage uncertainties, so we need to convert it back to an absolute uncertainty and then add them together. So in this case, if we convert it back to absolute uncertainty, we'll get 2.98 plus or minus 0.06854 plus 3.12 plus or minus 0.07488 meters. And if we add, so we will add both the values and the uncertainties, we'll get 6.1 plus or minus 0.14 meters. And if we round that to scale, we'll get 6.1 plus or minus 0.1 meters. Sorry, so now moving on to manipulating data. So right now I have a table of distance versus time for a ball to roll down, that should say a ball to roll down a ramp. So here we have a table. So this table is a representation of what you should be seeing in your actual investigation. So you have our distance, our uncertainty in distance, trial 1, trial 2, trial 3, our average, and our uncertainty in the time, process value, so that's square root of d, and process uncertainty is square root of d. So in this case, our time is proportional to square root of d. So therefore, in this case, to manipulate the data, we need to square root the distance. However, the distance has an uncertainty of 0.004. So in this case, we need to, the 0.004, that's an absolute uncertainty. So we need to convert that to a percentage uncertainty. Once we convert it to a percentage uncertainty, I have some examples on the next slide. So in this case, we see a square root relationship between the distance and time. We should square root all the distance values. When we square root an uncertainty, the percentage uncertainty halves. So okay, so sample calculation for this is for the average time. So average time is pretty simple. So you just add the uncertainties and then divide by a constant. So therefore, in this case, you should get 0.80 plus or minus 0.05 seconds. For the uncertainties, so that's square root of d. So first we need to calculate the percentage uncertainty, which is 0.004 over 0.350. However, we know that we need to, so when we convert it to a percentage, we will normally times by 100. But in this case, we're not going to times by 100 because we're not going to stay at a percentage uncertainty. Because at this stage, when we square root it, we know the percentage uncertainty halves, which means that our ratio also halves. But in this case, to convert it back to an absolute uncertainty, we need to divide by 100. So the multiply by 100 and the divide by 100, they cancel each other out. So in this case, we can just ignore the times by 100 and ignore the divide by 100. So in this case, we'll have the ratio, and the ratio is half because we're square rooting it. And we need to multiply by square root of 0.350. And in this case, the uncertainty is 0.003, and the unit is square root of meters. Alright, so here's a practice one. So speed versus tension and rope. So in this case, I'll tell you that F is proportional to speed squared. So F is proportional to V squared. Right, so this is the graph. So we have speed, uncertainty and speed, trial 1, trial 2, trial 3, average, uncertainty, that should say uncertainty in the fourth, process value, and process uncertainty. So try to fill out the process value and the process uncertainty. So pause the video now and keep watching after you're done. Alright, so the answer should look as the column the answer is now displayed. Right, so in this case we know that force is proportional to V squared. In this case we need to square all our V values, okay? because we know f is proportional to v squared. Okay, we need to square all our speed values. The absolute uncertainty is 0.4, but we know when we square an uncertainty, the percentage uncertainty doubles, and the actual value is squared. So to fill out our process value, so that's our processed value, all we need to do is just square everything in the speed column. So 10 squared is 100, 12 squared is 144, but it's been rounded due to uncertainty, it's been rounded. So 12 squared is 144, 14 squared is 196. So you just keep squaring it, and that belongs in your process value. For the uncertainty, we need to find the percentage uncertainty, we need to double it, and we need to convert it back to an absolute uncertainty. So in this case, we have 0. For our first column, we could say 0.4 divided by 10. That will give us the ratio. We need to multiply the ratio by 2, and once we multiply the ratio by 2, we will multiply it by the 10 squared, which is the speed squared, and we'll get the process uncertainty is 8 in that case. In the second case, we'll have 0.4 divided by 12. That's the ratio, and we're going to multiply the ratio by 2, and then multiply that by the square of 12, which is the speed squared. So we'll multiply it by 144, and we should get the process uncertainty is slightly greater than 10. I remember it came out to be about 11.2, if I'm not wrong. But if it came out to be 11.2, we need to round all our uncertainties to 1SF. So 11.2 rounds down to 10, and that's in the tens column. So therefore, we need to round our process value down to our tens column as well. So that's why I don't have 144, I have 140. The 140 is just the rounding down to the tens column due to uncertainty. And if you follow the same steps for 14, 16, and 18, you should get that all your process uncertainties should be all rounding down to 10. So I think the very last one was 14 point something, and 14 point something that still rounds down to 10 because it's to 1SF. And likewise, we need to round all our actual values. So the actual value needs to be rounded down to the tens value, to the tens column, because that's where our uncertainty is. Alright, so finding the theoretical. So after his investigation, Kevin found the gradients of force against speed. I should say speed squared. I don't know why it says speed. Okay. Kevin found his gradients, that's force against speed square, apologize, to be 0.025 plus or minus 0.007, and the unit is kg over m. And he maintained the radius of the swing to be 0.70 plus or minus 0.02 meters. And using the equation, centrifugal force equals to mv squared over r, trying to finding the mass with the uncertainty. Right, so in this case, we know that our gradient is basically the rise over run of the graph. So we know that force against speed squared, that's f over v squared, and that's equal to our gradient, which has been given. So therefore, our f over v squared, that's our gradient. So therefore, f over v squared, that equals to m over r. That's rearranging our equation. And therefore, we can actually substitute f over v squared as our gradient, which is 0.05 plus or minus 0.007. Bracket kg over m, that's a unit, and that equals to m over r. But in this case, we know r is 0.70 plus or minus 0.02 meters, and we can plug that in for r. And once we have all those values, we can rearrange and solve for our mass. So in this case, we have, if we convert 0.007 to a percentage uncertainty, we'll get 28%. So that's 0.025, the unit is kg over m, plus or minus 28%. And if we convert 0.02 as a percentage uncertainty of 0.7, we'll get 0.70 plus or minus 2.86%. The reason I converted it to a percentage uncertainty is because I need to multiply two percentage uncertainties. Once I multiply both sides by r, I need to multiply uncertainty by an uncertainty. When we multiply two uncertainties, we need to add the percentage uncertainty, okay? And that's why I converted both of them to percentage uncertainty, so we can add them. So once we move r to the other side, we'll have 0.025 plus or minus 28% multiplied by 0.70 plus or minus 2.86%, and that equals to our mass. So our actual value is just 0.025 times 0.7, which is 0.0175 kilograms, and our percentage uncertainty will just be 28 plus 2.86, and that gives us 30.86%. Okay, so now we have 0.0175 plus or minus 0.0175 kg plus or minus 30.86%. We need to convert the percentage uncertainty back to absolute uncertainty. So that's our percentage divided by 100 multiplied by 0.0175. And we should get 0.0175 plus or minus 0.0054 kilograms. Rounding it down to 1 SF, we'll get 0.018 plus or minus 0.005 kilograms. So in this case, if we round it down to 1 SF, it's down in the tens thousandths column, so we need to round down our actual value to the thousandths column as well. Alright, so data table 2. So in this case, we have a distance of separation and gravitational field strength. So I'm telling you that the gravitational field strength is inversely proportional to the distance squared. So G is proportional to 1 over D squared. So try to fill out this table. Okay, so just keep in mind that in the trial 1, trial 2, trial 3, everything is times 10 to the power of negative 9. Okay, so for our first one, it will be 133.2 times 10 to the power of negative 9, and etc. Alright, so try to find the process value and the process uncertainty. Alright, and this is the answer. Okay, so we should have our process value should just be the distance squared and then 1 over that distance squared. Okay, so in this case, for the first column, we'll have 0.050 squared, which is 0.05 squared. 0.05 squared. We should have 0.0025, and therefore if we do 1 over 0.0025, we should get 400. For our percentage uncertainty, we'll simply say 0.002 divided by 0.050. And that's our ratio. So in this case, our distance is squared. That's the first thing to do. The distance is squared. So once we square the distance, we need to multiply the percentage uncertainty by 2. Or in other words, we need to multiply the ratio by 2. So 0.002 divided by 0.05. That actually gives us a ratio 0.4. So we need to multiply, sorry, not 0.4, 0.04. Sorry. So the ratio is 0.04. We need to multiply by 2 because we're squaring the distance, so times by 2. And then we need to say 1 over something, the percentage uncertainty stays the same because it's a constant over uncertainty. So constant over uncertainty, the percentage uncertainty stays the same. So therefore we'll have 0.08 multiplied by 1 over 0.08 multiplied by 400. Okay, so that's basically gonna give us our uncertainty, which is actually 32, but rounds down to 30. So process value is 400, process uncertainty is 30 in that case. And if you follow the same process for the second one, so we have 0.02 divided by 0.1 times by 2, and then we multiply that percentage uncertainty, well not percentage, that ratio by 100 squared, by 100 we should get 4, and if we continue the same process, we should get 400, 144, 25, 16.0, 34, 1, 1, 0.3. So notice that for the last column, I added 16.0, and that's because the process uncertainty, when I round the process uncertainty down to 1 SF, we get 0.3, and that's in the tenths column, which means you have to round down the process value to the tenths column as well, so that's 16.0. Sorry, apologies for that. It's a calculation. So Kevin finds this gradient, so that's G over 1 over R squared. That's equal to 3.1 plus or minus 0.6 multiplied by 10 to the power of negative 10 newtons per kilogram meters squared. Using the formula, G equals to GM over R squared. Find the mass of the demonstration Kevin was using, so find big M. The universal gravitational constant I'll give you as 6.67 plus or minus 0.09 times 10 to the power of negative 11, and the unit is newtons meters squared over kilograms squared. Alright, so in this case, we know that our gradient is G over 1 over R squared. G over 1 over R squared, that's the same as saying G times of r squared, so that becomes gr squared. Notice that if we move the r squared to the other side, it becomes gr squared equals to gm. So small g times r squared equals to big gm. So gr squared is our gradient, and our gradient would, in this case, has been given to us as 3.1 plus or minus 0.6 times 10 to the power of negative 10. So that's our gradient. And notice that if we divide by the universal gravitational constant, we will find our mass, okay? So therefore, we need to divide the gradient by the universal gravitational constant. Notice that in this case, we're dividing two uncertainties, and according to rule number 2, when you divide two uncertainties, the percentage uncertainty is added. So in this case, we need to convert both of them to percentage uncertainties first. So for the gradient, it becomes 3.1 newtons per kilogram meter squared, plus or minus 19.35%. And the universal gravitational constant, it becomes 6.67 newtons meter squared kilogram squared, plus or minus 1.35%, bracket times 10 to the power of negative 11. Right, and so in this case, we can just divide the values and then add the percentage uncertainties. So mass actually becomes mass becomes 4.65 plus or minus 0.96 kilograms. And if we round that down, if we round the if we round the absolute uncertainty to 1SF, we'll get 1, and we need to round the actual value to the ones column as well. It becomes 5 plus or minus 1 kilogram. Right, so here's one more practice question. So Kevin is doing an investigation to find the relationship between the distance of separation of plates and the capacitor D and its capacitance C. The gradient of its linear graph C versus D is 0.0131 plus or minus 0.0002 farad meters. Our capacitance is equal to E naught ERA over D. And our E naught, which is our permeability of free space, that's 8.85 plus or minus 0.2 times 10 to the power of negative 12 farads per meter. And our area, area is 0.96 plus or minus 0.04 meters squared. So the equation of capacitance is shown above. Oh, sorry. Shoot. Apologize. Let me try. So I apologize for that. Okay, so doing investigation and alright, find the value of A. Why have I put A there? Okay, so for this question, just ignore the A there. Just ignore the A, and instead of A, the ER. That was supposed to be ER. I don't know why that happened. So, our dielectric constant, our ER, that equals to the ER equals to 1.00 plus or minus 0.01. Okay, that's our dielectric. So once again, use ER as 1.00 plus or minus 0.01. Okay, that's our dielectric constant, and then find the value of A. Right, so the gradient is C over 1 over D, or CD, and therefore CD equals to E naught ERA. So therefore CD is our gradient, so gradient equals to E naught ERA. And basically we just need to substitute our numbers in, so we know our gradient is 0.0131 plus or minus 0.002 equals to A, so A we don't know, times 1.00 plus or minus 0.01 multiplied by 8.85 plus or minus 0.2 times 10 to the power of negative 12. So because we're multiplying uncertainties, we need to add the percentage uncertainty, which means we're going to convert everything to percentage uncertainty. So once we convert everything to percentage uncertainty, everything on the right we can just multiply. So 1 multiplied by 8.85 times 10 to the power of negative 12, that is just 8.85 times 10 to the power of negative 12, and we can add the percentage uncertainty. So 1 plus 2.26 is 3.26%. So now, in order to find out A value, we can just divide both sides by 8.85 plus or minus 3.26% times 10 to the power of negative 12. And in this case, when we're dividing uncertainties, we need to add the percentage uncertainties, and we need to divide the actual values. So that becomes 0.0131 plus or minus 1.53% over 8.85 plus or minus 3.26% times 10 to the power of negative 12. And our answer should come out to be A equals to 1.48 meters squared plus or minus 4.79% times 10 to the power of times 10 to the power of 9. And converting, we should be, okay, so once you, sorry guys, this is pretty messed up. So 4.7, so converting it back to absolute uncertainties is 4.79 divided by 100 multiplied by 1.48. So therefore that comes out to be 0.07. So therefore our area equals to 1.48 plus or minus 0.07 1.48 plus or minus 0.07 meters squared times 10 to the power of 9. And that will be our final answer for that question. So that's all I have for uncertainties. Okay, so sorry about that last question, was a bit mumbo jumbo, but thanks for watching regardless, and I hope to see you all in the next one. Thank you. Bye.